Welcome back, everyone. Today we're going to talk about the next experiment, which is the synthesis of Stilbenedibromide from Stilbene. So the whole point of the organic chemistry lab was to teach you this, step-by-step synthesis until eventually we would reach hexaphenylbenzene. So what we've done already is we've purified our benzaldehyde, and we've been able to use the Wittig reagent to form Stilbene. So for today's experiment, what we want to do is we want to take Stilbene and react it with bromine to make our dibromostilbene, or Stilbenedibromide. So one super important note is in order to make Stilbenedibromide, you need bromine. Funny enough. And bromine is incredibly toxic. Like, if you inhale it, it could be fatal because it can cause severe burns. So it can mess up your lungs, it can burn your skin. So it is super important that if you ever have to work with bromine, be extremely careful with it. So usually the easiest way to break a double bond and add two bromines is by adding the dibromide. So liquid Br2 is a reagent that's incredibly volatile and super dangerous. So instead, we're going to use something that'll still get the job done and is a lot safer to use. So that is Pyridinium hydrobromide, perbromide, as you can kind of see here. So it's still dangerous. We can't get rid of all the danger when we want to work with bromine, but it can be handled a lot more easier because it's a solid. What is important to note is that it is extremely hygroscopic and will absorb moisture rapidly from the air and can become sticky, so it's better that we work with it pretty quickly and don't let it sit out too long. So the way that this Pyridinium hydrobromide perbromide is that it's in constant equilibrium between these two states, where the tribromide will kind of break off to make the dibromine that we need, while this forms a salt. So it's constantly going back and forth, which is why it's not as dangerous, but still dangerous, because we technically still are having this liquid bromine present. So once the Pyridinium hydrobromide perbromide forms our bromine, and we add our Stilbene, what will end up happening is the double bond will break and bind or attach itself to bromine, knocking off the other bromine, and will form the cyclic structure. The leftover bromine will then come and attack and break this bond so that we have the addition of two bromines. So here you can kind of see a better mechanism of what is going on. So once the double bond breaks, it's going to bend up and attach to the bromine, and we are going to have this cyclic structure. The leftover bromine will come on from the backside and go for an electrophilic attack and be able to bind, and it will form this trans state. So we can actually obtain 3 stereoisomers depending on which Stilbene we were using. So remember, we have both E and Z Stilbene, where most of it is going to be E. So here you can kind of see the 3 different products. We can have the RR configuration, the SS configuration, or the RS configuration. So this meso product is mostly going to be coming from that E isomer. What's really great though, is that it doesn't really matter which isomer we get, because all three of these isomers can be converted into diphenylacetylene for the next class, or the next lab. Alright, so just a quick little update. I read this a little bit wrong. So you actually will be receiving 4 products, not just 3. So you'll be getting the RS, the SS, and then the E configuration. You'll be getting a meso product, meaning you'll be getting SR and RS. So because they're meso though, they're pretty much the same, but in the end you will be getting 4 products. So for the procedure for the preparation of Stilbenedibromide, we're going to be needing 40 mLs of acetic acid, 2 grams of stilbene, 4 grams of Pyridinium hydrobromide perbromide, a hot plate, an ice bath to cool the reaction, a vacuum filtration device to collect the product, as well as filter paper in a Buchner funnel to separate the liquid from our solid product. So also during this lab, we could also have used thin layer chromatography to kind of investigate our product, but we will not be doing that. As for the melting point, we can't really measure the melting point of Stilbenedibromide because it's just way too high for our equipment and we won't be able to melt it. Can we reattempt a recrystallization? So we can't really, we can't really attempt a recrystallization because we have a starting mixture of E and Z stilbenes. So we can kind of expect a mixture of these 3 Stilbenedibromides, so they won't crystallize properly. But it doesn't matter because we can just collect the product and then convert them all to diphenylacetylene in the next step. So just a couple hazards in this lab. Remember, Pyridinium hydrobromide perbromide. Still extremely hazardous because it has bromine in it. It can cause those serious chemical burns as well as any respiratory and nasal irritation. The next would be glacial acetic acid. Glacial acetic acid is pretty hazardous and can cause some serious chemical burns as well as some respiratory and nasal irritation. And then the last thing would be methanol. So it's also known as wood alcohol, and it can just be toxic, so we shouldn't be ingesting it. It can also cause blindness. And just to kind of clarify, this is not the alcohol you find in your alcoholic beverages. Please try to be careful with it because getting it on your skin could irritate it. So because the reaction can be really dangerous and we have to heat this up at a pretty high temperature, the flask has to be heated, and so we need to have something to grip it. So remember, never grab hot glassware or any storage device with your hands. We have these clamps or prongs that we can use, or tongs, that we can use to hold beakers or bottles or flasks by their neck so that we can protect our hands from burning. All right. So after the experiment is done and we have purified our Stilbenedibromide, the next thing we want to do is check it using IR and NMR. So because stilbene and Stilbenedibromide, the only difference is the breaking of the double bond and the addition of the bromines, when we look at the IR spectrum, it's actually much easier to look at what has changed between the two. So the biggest difference is this peak right here. So this peak is what correlates to the double bond that was there originally. Once we add the bromines, it vanishes because now there is no more double bond. Something else to note is that the peak for the aromatics, while they are still in the right place, they are actually they're a lot smaller than what they were for stilbene. So these two peaks kind of indicate to us that we have purified the Stilbenedibromide. And if we look at the NMR, it's the exact same thing. What we're really looking for is the breaking of this double bond. So because when we have a double bond, sp2 hybridized carbons or hydrogens tend to be a little bit more downfield. So we can see it kind of here in this group of peaks. But once it breaks, this is no longer sp2, but now sp3 hybridized. So it will move upfield. So not only that, this hydrogen here will have its one neighbor over here. And so we can assume that this hydrogen is here. Yeah, so these hydrogens are this peak, and everything else is for the two aromatics. So this is how we can kind of figure out if we've actually purified our Stilbenedibromide. Alright, so now I just want to quickly go over how to find the limiting reagent when you're running a reaction. So the first thing that you want to do is first balance the equations. So here you can kind of see that the equation is balanced. So for every 1 mole of Stilbene, we are reacting it with 1 mole of Pyridinium hydrobromide perbromide. So now that everything is balanced, we need to find the amount of moles that we have of each starting compound. So first let's start with Stilbene. So since we're working with 2 grams of Stilbene, and the molecular weight of Stilbene is 180.25 grams per mole, all we do is divide it by these two together, and we get about 0.011 moles of Stilbene. Now if we move on to our Pyridinium hydrobromide perbromide, we do the same thing. We get the 4 grams of the Pyridinium hydrobromide perbromide and divide it by 319.82 grams per mole, as is its molecular weight. And we'll get 0.013 moles. That means if we were to run these two, what would end up happening is everything would be used up until eventually all of our Stilbene would be completely gone, and we'd still have about 0.002 moles of the Pyridinium hydrobromide perbromide. That means that Stilbene is our limiting reagent.